Welcome everyone to the first episode of the discrete mathematics series I'll be doing. I'll start off by teaching graph theory, and today I will introduce graphs, different ways to reverse graphs, and connected components and connectivity. To start off, a graph is an object with vertices connected by edges. Formally written, we can see this as a graph G is going to equal a tuple with a set V and a set E. V is just going to consist of all vertices in the graph. Here, V1, V2, up to Vn, and E is a set of sets, where each set is an edge which consists of a pair of two vertexes. Here we have Vx0, Vy0, Vx1, Vy1, and so on. To draw it out, I just made a miscellaneous graph. We have vertex, edge, and so on. As an example, I made a graph. Here we have V and E, where V is a set with three vertexes, and E has three edges in it. So we have V1 here, then we have V2, and now we have V3. From V1 to V2 I have an edge, from V2 and V3 I have an edge, and from V3 and V1 we have an edge. Here I drew it to be a triangle, but it could really be any shape you want. And some different ways to reverse it is going to be walks, trails, and paths. This is not the total list. There's many more ways to reverse a list, but these are some of the main ones that we'll use to build on upon later episodes. Here, a walk is a finite alternating sequence of vertices and edges. So, for example, we could have V1, E1, V2, E2, V3, E3, and back to V1. I'll just draw this out so you can see. We start off with V1 down to this edge, V2 down to this another edge, now V3, and all the way back into V1. I didn't label it before, but we just imagine this as E1, E2, and E3. So that's just a walk, just some traversal through the graph. And a trail is just a walk with no repeated edges, and the path is just a walk with no repeated edges and vertices. Here I'll just draw out some examples. We'll go to V1 to V6 to V5, V2, V3, and V4, back to V5, V7, V4, and then back to V5. You can see here I repeated edges and vertices. In the trail, we'll go from V1, V6, V7, V5, then V4, V3, V2, then V5, then V6. Cannot continue because after that I'll repeat an edge, which is not allowed in a trail. But here I repeated V5, as you can see. Now in the path, V5 to V7 to V4 to V3, the V2, V1, then V6. Here I have to stop or I'll end up repeating a path, an edge, or a vertice. Now, connectivity components. A connected graph, the formal definition is for every vertex V in W and G, there is a walk from V to W. What this means is that if you choose any two vertices in a graph, there will be a walk from those two components. But really visually, that just means there's one graph. There's not just some miscellaneous vertex or some graph out in the open. This is all, if there was just two components, this would still all be one big graph. Here, a component, I'm just going to say visually, is a section of the graph that is disconnected from the others. We'll go back here. This is a component, and this is a component. And I wrote here that's disconnected, but also if we have one graph that is a connected graph, that is also technically a component, but it's just a connected graph, so there's really no need to state it because it's trivial. Here I'll just make some examples. We have some vertices here. Connect them. That's a connected graph right here. Right here. This is also connected graph trivially. And here, this is also connected graph. Components. Now, we can imagine, even though I'll be drawing it separately, that this is all one graph. And if you wrote in mathematical notation, it would be easier to understand that it's one graph. But here, there's just one graph. These are also two components. And usually components can be labeled as H, like H1 and H2. And that is it. I've went over graphs, different ways to reverse it, and components and connectivity.